Yeah. Okay. 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 So, okay. So last time we defined the harmonic measures on the boundaries of geodesic balls, right, in a Riemannian manifold. So this follows the existence of these measures follows from the solution to the Dirichlet problem, right? So we know that for any continuous function phi on the boundary of the ball, there is a unique solution to the Dirichlet problem with boundary value phi. So it's C2 on the ball and C0 on the closure of the ball. The Laplacian of U is 0 in B, and U is equal to phi on the boundary of B. And this solution is unique. And the solution satisfies the maximum principle. Okay. And so we can define a linear functional on the space of continuous functions on the boundary of the ball. Phi goes to, for every point x in the ball, we can define a linear functional. Phi goes to u phi at x. Okay. The value of the harmonic extension of phi at x. So we saw that from the maximum principle, this functional is bounded of norm less than or equal to 1. And the maximum principle also implies that it's a positive functional. So if phi is greater than or equal to 0, then Tx of phi is greater than or equal to 0. So it's a positive bounded linear functional on the Banach space C0 of del B. And therefore, by Riesz representation, it defines a positive measure. And since this functional takes the constant function 1 to 1, that means this is a probability measure. So for every point x in the ball, we get a probability measure on the boundary of the ball, which we call the harmonic measure of the ball with respect to the point x. Okay. All right. So today we'll prove a couple more properties of these harmonic measures. So first of all, if U is C2 on the ball and C0 on the closure and is subharmonic in the ball, so that means the Laplacian of U is greater than or equal to 0, then we can say that U of x is less than or for any x in the ball, U of x is less than or equal to the average of U over the boundary of the ball with respect to the harmonic measure based at x. Okay, so for a harmonic function, we have equality here. For a subharmonic function, we have this inequality. Okay. So in other words, what is this saying? The right-hand side here, this, by definition of the harmonic measures, the right-hand side here is actually the unique solution of the Dirichlet problem with boundary values u on the boundary of the ball, right? So if I restrict u to the boundary of the ball and I extend it to a harmonic function inside, then what I find is that if u is subharmonic in the ball, then u is less than or equal to the harmonic extension of its boundary values. Okay. All right. So in other words, u and this harmonic function, they agree on the boundary of the ball, and the subharmonic function is less than or equal to the harmonic function inside. So this is where the terminology subharmonic comes from. In other words, it's bounded above by a harmonic function with the same boundary values. Is that clear?
Yes, sir.
Right? Okay. So the proof is simple. So you let phi be the boundary value of u restricted to the boundary of the ball. So then look at u minus the harmonic extension of phi, u phi. So since u phi is harmonic and u is subharmonic, this is subharmonic, and u minus u phi is less than or equal to 0 on the boundary of the ball. And then for subharmonic functions, well, we proved the weak maximum principle for elliptic operators on a bounded domain in Rn, right? And so from that, it will follow that for a subharmonic function, we also have the maximum principle on a geodesic ball in a Riemannian manifold, since it embeds as a bounded domain in Rn, right? So we can apply the maximum principle for operators in Rn. And so, so this u minus u phi is less than or equal to 0 on the boundary of the ball, and therefore it's less than or equal to 0 on the ball. Okay, by the weak maximum principle. And this means, therefore, that ux is less than or equal to u phi x, and that's exactly the integral of phi xi with respect to harmonic measure at x, which is the integral of u with respect to harmonic measure at x. Okay. All right. So now we're going to state the Harnack-Yau inequality, which is, if you like, a sharper version of Harnack's inequality, the classical Harnack inequality for positive harmonic functions in Rn. This is a version for Riemannian manifolds, which in a sense is sharper because Harnack gives a bound on the values of the function. This Harnack-Yau inequality will give a bound on the gradient of the function, which will imply the bound on the function. So it's a sharper bound in that sense. So
Sir?
the Harnack-Yau inequality is, yes.
Sir,
Yes.
can you recall the Harnack inequality? Hello.
Yes, yes. So see, the classical Harnack inequality comes from the Poisson formula. So say on the unit ball in Rn, right?
Yes.
We derived the Poisson kernel for this unit ball, right?
Right.
So it was, let me remember, 1 minus, let me just check the formula. 1 second. We derive this much earlier. Yeah, 1 minus norm x squared divided by norm x power n.
Yes.
Into a constant, I think, 1 over Cn, the volume of the unit sphere.
Right.
So
Yes.
let me just check the. Yeah, so, okay, fine. So into 1 over Cn, right. Okay. So here x belongs to the ball and xi belongs to the boundary of the ball. And so now suppose u is, as usual, C2 on the ball and C0 on the closure. And suppose in addition that u is positive or non-negative and harmonic. Yeah. Then if this is the origin and if I take a point, say x at distance r, then what can I say about u of x? So I'll get upper and lower bounds in terms of u0, because u of x is so 1 over Cn integral over boundary B, 1 minus norm x squared over over norm x minus xi power n d sigma xi, right? And here I can bound into u of, sorry, into u of xi. And the point is I can bound the Poisson kernel, right? So from above and from below. So first of all, this 1 minus norm x squared, this is less than or equal to 1, let's say. And this norm x minus xi whole squared, this norm x minus xi is greater than or equal to 1 minus r, right? So this will be less than or equal to 1 over 1 minus r power n, right? Because xi is on the boundary and x is inside the ball of radius r. So this norm x minus xi is at least 1 minus r, right?
Right. Yes.
So this will be less than 1 over 1 minus r power n. And then this integral 1 over Cn u xi d xi by the mean value property, that's u0. Okay. So I have an upper bound of the values inside the ball of radius r in terms of the value at the center, right? And similarly, I have a lower bound also. So
1 plus.
this will be this 1 minus norm x squared. This is greater than or equal to 1 minus r squared. So I'll get a 1 minus r squared. And this norm x minus xi, this is less than or equal to 1 plus r. So I'll get 1 plus r to the n. And then I'll get u0. Okay. So this is the classical Harnack in Rn. Okay.
Okay. Okay. Yes.
So this gives you bounds on the values of the function in terms of values at the center. But this only holds when the function is non-negative, right? This
Right.
only holds when
Right.
the function is
Yes.
non-negative. These inequalities
Non-
we get because this usi is non-negative, right? So therefore I can get these inequalities. Is this clear?
Yes, sir. Yes. Fine. Hmm. Yes, sir. Yes.
Okay. So yeah. Utsav, is this okay? Yeah.
Yes, sir.
Yeah. So the classical Harnack inequalities give you bounds on the values of the function in terms of the values at the center. The Harnack-Yau inequality is sharper because it's going to give you bounds on the gradient of the log of the function, which will imply the bounds on the function. Okay. Okay, so let me state the Harnack-Yau inequality. So first, 1 second. Okay. So the Harnack-Yau inequality is the following. So let B be a geodesic ball of radius r in a Riemannian manifold, and let mod x be the distance from the center, say O, to x. And suppose the sectional curvature in the ball B is bounded below by some constant minus b squared. Okay. Actually, Yau proved it with a lower bound on Ricci curvature, but I haven't defined Ricci curvature. And the proof, well, needs a few more facts. If you want to use the version with Ricci curvature bound, then yeah, it needs a few more facts. So for simplicity, let me assume the sectional curvature is bounded below. This implies a lower bound on Ricci curvature. Okay.
Okay.
So let me assume it's bounded below. And then there is a constant C, which depends only on the dimension and the lower bound on the sectional curvature, such that for any positive harmonic function u in the ball B, we have that the norm of the gradient of log u, so u is positive, so I can look at its logarithm. So the norm of the gradient of log u is less than or equal to this constant into 1 over r minus mod x. Okay. So this bound blows up as you go towards the boundary of the ball. All right. But it doesn't blow up too fast. It blows up like 1 over the distance to the boundary. Okay.
Okay.
Is this
Yes, sir.
yeah? So why is this sharper? Because a bound on the logarithmic gradient, the gradient of the log, is going to give you a bound on ratios of the function, ratios of values of the function, right? By integrating.
Right.
See, here the Harnack inequality is giving you a bound on ratios actually of the function, right? Ux divided by u0 is bounded above and below by some constant. So the ratio of the function is going to come when you integrate the logarithm, right? So that's what we'll get here. So as a corollary, we get this following Harnack inequality, that with the same hypothesis and notation as above, we have for any non-negative harmonic function u on B, that ux is less than or equal to e to the c times log 1 over r minus mod x into u0, and greater than or equal to e to the minus c times log 1 over r minus mod x u0. Right? So this is like the classical Harnack inequality. All right? Okay, and this will follow from the Harnack-Yau inequality just by integrating. So if you integrate, so that's the proof, you integrate the gradient of the function log u plus epsilon. So if u is non-negative, I may not be able to take the log immediately because it could vanish at some point. So let me just add a small epsilon to u. So I look at u plus epsilon, then I can take the log. So I look at log u plus epsilon. I integrate this along the geodesic from 0 to x.
Mm.
Okay, from the center to x.
Mm.
Right. And so then we use the Harnack-Yau inequality. The gradient is bounded by this 1 over r minus mod x. So when I integrate 1 over r minus mod x, I'll get log 1 over r minus mod x, right?
Mhm.
So, and when I integrate the gradient of log u plus epsilon by the fundamental theorem of calculus, I'll get log of ux plus epsilon minus log of u0 plus epsilon, right?
Mm. Yes.
This is just the fundamental theorem of calculus, right?
Right. Yes.
Utsav? Yes, Utsav, is this okay?
Yes, sir.
Yeah. I mean, what I mean is I'm just looking at an integral over the geodesic. Fundamental theorem of calculus just means the integral over the geodesic from 0 to x of grad of some function v of gamma t inner product with gamma prime t dt. Gamma is this geodesic from 0 to x. This is equal to Vx minus V0, right? This is the fundamental theorem of calculus, yes?
Yes.
So you apply this with V equal to log of u plus epsilon, right? Okay, and then this left-hand side you can bound because you bound the gradient of V, right? The gradient of V is bounded. So this will be bounded by, you have the modulus of the left-hand side is less than or equal to the integral from 0 to mod x of this constant times 1 over r minus t dt, right? By the Harnack-Yau inequality. Is this clear?
Yes, sir.
Yes.
Yeah. So
Yes.
this is equal to c times log 1 over r minus mod x. Okay. Yes, is this all right?
Yes, sir.
Okay. Just calculus, right?
Mm.
So you get this bound and then you take exponentials,
Mm.
right? So this means this is log of ux plus epsilon divided by u0 plus epsilon. So mod of log is bounded by this. So that gives you two inequalities and then take exponential. So you get ux plus epsilon bigger than or equal to u0 plus epsilon into e to the minus c log 1 over r minus mod x and less than or equal to e to the c into log 1 over r minus mod x into u0 plus epsilon. Now just let epsilon tend to 0 and you're done. All right?
Yes.
Yes, sir.
That's it. Okay. So that proves the Harnack inequality from the Harnack-Yau inequality. And as a corollary, we get an estimate on the harmonic measures with respect to any point x in the ball compared to the harmonic measure with respect to the center of the ball. Okay, so we have this these bounds that if x is any point in the ball of radius r, then the harmonic measure with respect to x, mu xb, is less than or equal to 1 over r minus mod x to the power c into mu 0, the harmonic measure with respect to the center, and also greater than or equal to r minus mod x whole power c into mu 0 b. Okay. So harmonic
Right.
measure with respect to any point x is bounded above and below by constant multiples of the harmonic measure with respect to the center. Okay. Okay, so as you go towards the boundary of the ball, the harmonic measure cannot blow up faster than a polynomial in the distance to the boundary, basically. Right? It's like a polynomial in 1 over distance to the boundary.
Okay.
Yes, sir.
Which is exactly this sort of polynomial growth near the boundary is exactly what you have for the classical Poisson kernel, right? Look at this. As x converges to xi, the Poisson kernel blows up like a power of the distance to the boundary, right?
Yes, yes.
Right?
Right. Right.
Right? It blows up like a power of the distance to the boundary. So here, abstractly, what is the Poisson kernel in a manifold, in a geodesic ball? It's the Radon-Nikodym derivative, right? D mu xb divided by d mu 0b. That we're getting an upper bound. For its sup norm, it is less than or equal to 1 over r minus mod x power c, right? So it can, again, it's like in the Euclidean setting, it can blow up at most like a polynomial in the distance to the boundary. All right.
Yes.
Yes, sir.
Okay. So yeah, so in that sense, the Poisson kernel is similar to the Poisson kernel of the Euclidean space. Okay. The abstract Poisson kernel is going to be similar. Okay. So in particular, what do we get? That for all xy in the ball, the harmonic measures are mutually absolutely continuous, right? Okay.
Yes.
So mu x is absolutely continuous with respect to mu y, and also mu y is absolutely continuous with respect to mu x. So actually, this result, I mean, to prove that they're mutually absolutely continuous, that follows from more general results, namely the existence of Green's functions for the ball. But I mean, the existence of Green's functions is non-trivial. At least I think it's somewhat non-trivial. So, because it follows from the existence of the heat kernel for the ball, the Dirichlet heat kernel for the ball, with boundary conditions 0. So I can say a bit about Green's functions and the Poisson kernel. We didn't have time to talk about this last time. So let me just say, so what is the Green's function for the ball? So suppose B is a ball in M. Yeah. Ball in Riemannian manifold. Here, I mean, you don't need to take a ball as such. You can just take a domain. Let me be more general. You can take a domain, okay? So then you have the Green's function. So if I take a point X in the domain, so let me take a domain. So the Green's function for D with pole at X is the unique function G X T, say, from the domain, the closure of the domain to 0 plus infinity, such that the Laplacian of the Green's function is minus the Dirac mass at x. So this is the distributional Laplacian, all right?
Hmm.
And so that means outside the point x, this is harmonic, right?
Hmm.
Because the Dirac is supported at x. So outside the point x, the Green's function is harmonic.
Right.
And on the boundary, the Green's function is 0. Okay. So uniqueness of such a function follows from the maximum principle, right? Because if you have two such functions, then they have the same distributional Laplacian. So the difference of those two functions will be harmonic and it vanishes on the boundary. Therefore, it will be 0 everywhere, right?
Hmm. Yes.
Okay, so if such a function exists, then it is unique. Is this all right?
Hmm.
Yes, sir.
Okay. Okay. And actually, how can one get such a Green's function? It turns out that this Green's function you can get from the heat kernel of the domain. So gxd of y actually is equal to integral from 0 to infinity p sub d of t xy dt. Okay, so where p sub d, this is the heat kernel. So that means it satisfies del t of p sub t of p sub d of t x dot is equal to, so Laplacian in the y variable of p sub d t x dot. Okay. And you have these boundary conditions in the time and space variables. So p sub d of t x dot, this converges to, in the sense of distributions, to the Dirac mass at x as t tends to 0. And p sub d of t x y, this is equal to 0 for all y in the boundary of the domain. Okay, so this is called the so construction of such a function is quite non-trivial, but this is called the Dirichlet heat kernel for the domain. Okay, this p sub d of this is called the Dirichlet heat kernel of D. Okay, so the Green's function you can get by integrating the Dirichlet heat kernel of the domain. All right.
This heat kernel is unique.
Yes, this is unique. Yeah, this is unique. This exists and is unique. That's quite a non-trivial result. All right. So once you have the Green's function, then you can get a Poisson formula, right? Using Green's formula,
Hmm.
right? So now if
Normal.
U belongs to C2D intersect C0D closure, you use Green's formula that integral over D u Laplacian gxd minus Laplacian u gxt and so on. So we're almost out of time. Let me stop this session and start another one. Okay. Okay. Right. So once you have the Green's function with pole at x for the domain D, then you apply Green's theorem, right? So this integral over the domain D, dvol, is equal to the integral over the boundary of D of u into the normal derivative of the Green's function minus the Green's function into the normal derivative of u ds. Okay. And of course, well, the Green's function is going to have a pole at x. So actually what you'll do is you're going to integrate over the domain D minus a small ball around x, right? This is what we've done, right? When we've applied the Green's formula, right? Yes, when we were proving the mean value property for harmonic functions in harmonic manifolds, we integrated over an annulus, right? A large
Right,
ball,
yes.
a small ball, and then you let the radius of the small ball tend to 0, and you take a limit, right? So you'll have to do the same sort of thing here. But just formally, what do you get? The Laplacian of the Green's function is minus the Dirac at x. So this u times this Laplacian will be minus ux, right? This integral will be minus ux. And then this Laplacian u, this term vanishes because u is harmonic. So on the left-hand side, you get minus ux. And on this side, the second term vanishes because the Green's function is 0 on the boundary. So you just get the first term. So you get minus ux is equal to the integral over boundary D of u xi normal derivative of the Green's function. Well, n of xi ds of xi. And so you just take the minus sign to the other side. And so you get the Poisson formula in terms of the normal derivative of the Green's function. Okay. Minus the normal derivative of the Green's function. Okay. So that tells you that the harmonic measure is going to be this measure, right? The normal derivative of the Green's function into the surface area measure of the boundary, right? This measure is equal to d mu x d. Okay, so now harmonic measure of the domain D with respect to the point x. So this is a measure on the boundary of the domain. Okay, so this is defined similarly to how we defined harmonic measure for the geodesic ball. All you need is that the Dirichlet problem is solvable, right? Once you know that the Dirichlet problem has a solution, then you define the harmonic measure by the same way. For each point x in the domain, you have a linear functional, right? Which is you take any continuous function on the boundary, you take its harmonic extension and evaluate it at x, right? By the maximum principle, again, this is going to be bounded positive linear functional, and the constant function 1 goes to 1, so it's going to be a probability measure. This is the harmonic measure. All right. Yeah, so there's nothing special about a geodesic ball. All you need is a domain for which the Dirichlet problem is solvable. Okay. So then you'll have a harmonic measure on the boundary of that domain. So we will show later using the Perron method that for any domain in a Riemannian manifold, a precompact domain with C2 boundary, okay, the Dirichlet problem is solvable. Okay. So we just need a C2 boundary and then the Dirichlet problem will be solvable.
Sir,
Yes.
this existence of this Green's function is this is always possible for any domain, or is it
For any precompact
possible
domain.
only?
Yeah, for any precompact domain. Yeah.
Oh,
With smooth boundary. Take it with C2 boundary.
yeah.
With smooth boundary.
Okay.
You just need existence of the Dirichlet heat kernel,
Heat kernel.
and then by integrating the Dirichlet heat kernel, you get the Green's function of the.
Green's.
So this tells you that the harmonic measure is absolutely continuous with respect to surface area measure of the domain, right?
Mm-hmm.
And the Radon-Nikodym derivative is minus the normal derivative of the Green's function, right? So mu xd is absolutely continuous with respect to the surface area measure, Lebesgue measure of the boundary, and the Radon-Nikodym derivative is minus the normal derivative of the Green's function with polar x. Okay. So if you want the Poisson kernel of the domain, right, what is the, so this will tell you that, see, all of these measures are mutually absolutely continuous with respect to the Lebesgue measure on the boundary. And so they're all mutually absolutely continuous. And so if I fix a base point O in the domain B, then the Poisson kernel of the domain D is the function P of x xi. This is the Radon-Nikodym derivative of harmonic measure with respect to x versus harmonic measure with respect to the origin. Okay, evaluated at xi. Okay, and so this is therefore a ratio of normal derivatives of Green functions, right? So this is the formula I wrote at the end of last time, right? Is this clear?
Yes, sir.
Yes.
Yeah, and so then the Poisson formula becomes once I fix the base point and the harmonic measure with respect to the base point, then my u of x, if u is harmonic and continuous up to the boundary, this is integral over boundary d u xi d mu, sorry, d mu x t of xi. But what I can do is I can divide this by d mu 0 d and multiply by d mu 0 d. And so this becomes the integral over boundary d u xi px xi d mu 0 d of xi. Is this okay? Right?
Yes, sir.
Yes, sir.
Yeah, so this is the Poisson formula then. So you have this Poisson kernel.
You have to give ds xi, right?
No,
No?
no. See, the original formula is ux is equal to integral u xi d mu x d of xi, right?
Yes.
That's by definition of the harmonic measure mu x d.
Right.
Then I just divide by mu 0 d and I multiply by mu 0 d, right?
Okay.
Right. So what I get is the Radon-Nikodym derivative into d mu 0 d, right?
Okay.
And that Radon-Nikodym derivative I'm defining to be the Poisson kernel, pxi.
Okay.
So, I mean, Rudra, you can write it in terms of ds also. In terms of ds, then it's just the coefficient is just this minus normal derivative of the Green's function with pole at x. This formula. If you want to write it with ds, then it's this formula. Yeah. So, I mean, the reason I'm not writing it with ds is because typically, what we want is a formula in the limit when, let's say, you take balls which are getting larger and larger, and then so the surface area of those balls is going to of the boundaries is going to infinity, right? So this ds measure is getting unbounded. The mass
Right.
of ds is going to infinity, but these harmonic measures d mu 0 d, these are probability measures. So these we can take a weak limit, and these will converge to a probability measure on the boundary at infinity,
Okay.
which will be the harmonic measure on the boundary at infinity. So in this formula, we can pass to the limit, you see.
Okay.
So, I mean, this will be the Poisson kernel of the finite domain, D. And the idea is to show, so this is what Anderson and Schoen show, is that this Poisson kernel of the finite domain, this converges to a Poisson kernel for the whole space.
Okay.
So, I mean, if we tried to do that with this formula with ds, then this ds would go to infinity and this normal derivative would go to 0. So you can't take a limit really. You see, the coefficient is going to, this is going to 0, this is going to infinity. So that's why it's maybe better in general to take it with respect to harmonic measure mu 0 d instead of ds.
Okay.
Sir.
Does that make sense? Yes.
So this
Yes.
Poisson kernel is dependent on my base point O, right?
Yeah, you fix a base point,
Yes.
sure. And then you get a Poisson. So for a ball, the natural base point is just the origin of the
yes.
ball, the center of the ball. For a ball, the natural base point is the center of the ball. So let me just make a remark to, so these things might seem a bit abstract. So, I mean, in a very classical setting, in complex analysis, when you study harmonic measures, so suppose D is a Jordan domain. So that means a domain bounded by a Jordan curve in C in the complex plane, right? So So this is the domain D. What is the harmonic measure with respect to X on boundary D? Can you say what this will be in terms of complex analysis? So what do you know about a simply connected domain in C, which is not all of C, of course?
Riemann mapping.
Isomorphic to the disk.
The Riemann mapping theorem, right? The Riemann mapping theorem. So you have a Riemann mapping. Let's take it going in this direction. Say F. And I can choose it to map the origin to X, right?
Yes.
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 Now, if I have any harmonic function on the domain D, then since holomorphic composition with holomorphic functions preserves harmonicity, this U composed with F will be harmonic on the unit
Right.
disk, right? And so the value of U composed F at the origin, I know this is a harmonic function on the disk, continuous up to the boundary. Let me assume if U is continuous up to the boundary, then U composed F will be continuous up to the boundary. Because F, if D is a Jordan domain, there's a theorem of Carathéodory that the Riemann mapping extends to a homeomorphism from the closed unit disk to the closed domain. Okay, it extends to the boundary, mapping boundary to boundary homeomorphically. And so then the value of U composed F at the origin by the mean value property is just the average with respect to Lebesgue measure on the circle S1, right? Right. So if I say d lambda is the Lebesgue measure on the normalized Lebesgue measure on the circle, d theta by 2 pi, right?
Right.
Then U of X is what? It is U of F of 0. So U composed F of 0, which is the integral over S1 of U composed F of xi d lambda xi, right? This is the mean value property. But this is the same as the integral over the boundary D by making a change of variables, right? Say eta equal to F of xi. And this becomes an integral over boundary D of U of eta. And this d lambda, instead, this will become d f star lambda, right? The push forward of lambda. D f star lambda of eta, right? Where here, so F is the Riemann mapping such that F of 0 equal to X. So what does that mean? That means that this measure, F star lambda, is the harmonic measure of this domain with respect to X, right? That means that mu xt is equal to F star lambda.
Yes,
Is this
sir.
clear?
Right.
Okay, so you take the normalized Lebesgue measure on the circle, push it forward to the boundary by the Riemann mapping. That gives you the harmonic measure on the boundary of the domain. Okay. So this is so estimates for conformal mappings will give you estimates for harmonic measure.
Right,
Okay.
right.
If you have estimates on the derivatives of conformal mappings near the boundary, this is very classical. That's why I'm just saying this. Like, this is the relation with complex analysis. So if any of you are interested, this is very classical. There's very classical. So a lot of work on this. Yeah. So So harmonic measure in the complex plane is very well studied. Okay, for domains in the complex plane, it's very well studied. Yeah. Okay, so this is a concrete example of harmonic measure, right?
Yes.
Yeah. Okay. Okay. So now let's come back to this. Yeah. So we had this. So any questions about this?
Yes.
This is fine. Yeah.
Fine.
Yeah. Okay. Oh, fine. So now let's come back to the proof of this corollary, that harmonic measure with respect to a point x in the geodesic ball is bounded above and below by these constants depending on x, which are like polynomials in 1 over distance to the boundary, right? So the proof is just by this. It follows from this Harnack inequality, right? So which we have here. So you take any continuous function on boundary B, which is non-negative. So then by the maximum principle, its harmonic extension is also non-negative on the ball. And therefore we can apply the Harnack inequality, right? So we get that the harmonic extension u phi of x is less than or equal to 1 over r minus mod x to the power c into u phi of 0 and greater than or equal to r minus mod x power c u phi of 0. And this u phi of x, this is the integral of phi with respect to the harmonic measure based at x, and this u phi 0 is the integral of phi with respect to harmonic measure based at 0. So since this is true for all phi, so that means the measures satisfy this corresponding inequality, right? Yeah.
Yes. Fine.
Okay, if you know the integrals of two measures with
Hmm.
respect to all non-negative continuous functions satisfy some inequality, then the measures satisfy the
Right.
same inequality,
Yes.
right? So okay, so that's how we get this
Mhm.
inequality between the measures. That's it.
Mhm.
So as a corollary, what we get is that the harmonic measure has full support. The support of the harmonic measure is the whole of the boundary of the ball. So again, this, if you know about the Green's function of the ball, you can maybe try and prove it that way, because you know that the harmonic measure is absolutely continuous with respect to Lebesgue measure of the boundary, and the Radon-Nikodym derivative with respect to Lebesgue measure of the boundary is minus the normal derivative of the Green's function. So to show that it has full support, you just have to show that this normal derivative does not vanish on any open set in the boundary, right?
Right.
You just have to show it doesn't vanish on any open set in the boundary. But that itself is a bit non-trivial. Unless you have some estimates on this normal derivative, you know, that's non-trivial in general, right? So it's not, a priori, it's not clear that even with this formula for the harmonic measure as normal derivative into the surface area measure, it's still not clear that it has full support, right? Because this normal derivative could vanish on some open set in the boundary. Then the measure of that open set harmonic measure would be 0, right? So it would not have full support. So it's not clear. Unless you have some estimates on the Green's function, it's not clear. So those estimates are true, but they're non-trivial. So we're not going to do them. So instead, we have a soft argument to show that the harmonic measure has full support. So you take any point xi in the boundary of the ball, and let u in the boundary of the ball be a neighborhood of xi in the boundary of the ball. Okay. So then we have to show that for any x, mu x of u is positive, right? We have to show mu x of u is positive for any x in the ball. So now what we can do is take phi, a continuous function on the boundary of the ball, such that phi is less than or equal to the indicator function of the open set U on the boundary of the ball, okay? And phi of xi is equal to 1, okay? So phi is like a bump function, basically, supported in a neighborhood of xi, okay? With support contained inside U, all right? Okay, so then take the harmonic extension of phi, U phi. So U phi of x converges to phi of xi, and we're assuming phi of xi is 1. So for x in the ball close enough to xi, we have that the harmonic measure mu x of U. So this is the integral of the characteristic function of U, d mu x. This is going to be greater than or equal to the integral of phi d mu x, since phi is less than or equal to the characteristic function of U. And the integral of phi d mu x is the harmonic extension U phi at x. And this converges to phi of xi. So for x close to xi, this is greater than a half, right? Which is positive. In particular, it's positive. So that means if x is close enough to xi, then the measure mu x of U is positive. Therefore, by the previous corollary, mu y of this open set U is positive for all y in the ball, right? Because these measures are mutually absolutely continuous for all x and y, right?
Yes.
Okay, so if I know it for x close to U, close to xi, then it's also true for all y in the ball, okay? Is this clear? Yes?
Yes,
Uh,
yes.
Yes.
Okay. Okay, so therefore the support of the harmonic measure is the full ball, full boundary. Okay, so once we have this, why am I doing all this? Because I want to prove maximum principles for subharmonic functions. Okay, so we proved a maximum principle for a domain which embeds into Rn, right? Because then you can just use the weak maximum principle for elliptic operators in a bounded domain in Rn. But as we've seen, of course, domains in Riemannian manifolds, they may not embed into Rn, right? They could have non-trivial topology which prevents it from embedding into Rn. But naturally, you still want to say the maximum principle should still hold, right? So we are going to prove the maximum principle using harmonic measures on geodesic balls. Okay. This will be similar to the proof of the maximum principle for subharmonic functions in Rn for the Euclidean Laplacian using the submean value property for subharmonic functions. Okay. So it's similar to the proof of that. Because you see, we have the submean value property for subharmonic functions. That is this lemma, right? Ux is less than or equal to the integral of u xi with respect to harmonic measure. This is a submean value property, right? Except instead of, like surface area measure, it would be in Rn if x is the center of the ball. Instead, we have the submean value property with respect to harmonic measure. Okay. Just like harmonic functions satisfy the mean value property with respect to harmonic measure, right? So subharmonic functions satisfy the submean value property with respect to harmonic measure. So first we get, using harmonic measures, we're going to show the strong maximum principle. So let D be a precompact domain in a Riemannian manifold. If U is a C2 function on D, which is subharmonic and attains its maximum at some point of D, then U is constant. Okay, so this is the strong maximum principle. And the proof is similar to the proof in the Euclidean setting, where in the Euclidean setting, you would have used the submean value property with respect to, Lebesgue measure on the boundaries of balls. Here we're going to use the harmonic measures. So let M be the supremum of U over the domain D. And so we're assuming that U attains its maximum. So let E be the set of X where U attains its supremum, okay? Where Ux equal to M. So we're assuming U is C2, in particular, it's continuous. So, so this set E is closed, right? Because U is continuous. And we want to show, and it's non-empty by hypothesis. So we want to show it is open, right? And the proof of this is using the submean value property, just like in Rn. So suppose X is a point in E. So Ux is equal to the maximum M. So then you take any ball of radius R whose closure is contained in the domain D, a ball around X of radius R. So then we know that right, on the boundary of the ball, U is less than or equal to U of X, right? Because X is a point where U attains its maximum. So U is less than or equal to Ux on the boundary of the ball. But on the other hand, Ux, by the submean value property that we proved for subharmonic functions with respect to harmonic measure, Ux is less than or equal to the integral over the boundary of the ball of U with respect to harmonic measure based at X, right? So since this mu X is a probability measure, right, this implies that U has to equal Ux almost everywhere on the boundary of the ball, right, with respect to this harmonic measure. Yes?
Yes.
Okay, I mean, look, if you want, what is this? This U minus Ux is a function which is less than or equal to 0. And then in this inequality, since this is a probability measure, I can take this Ux into on the other side, inside the integral. I get that the integral of U minus Ux is greater than or equal to 0, right? But U minus Ux is less than or equal to 0 everywhere. Therefore, U minus Ux has to equal 0 almost everywhere with respect to harmonic measure. Okay. Now I get to use the fact that the harmonic measure has full support. Right. This U equal to Ux almost everywhere on the boundary of the ball. This is almost everywhere with respect to harmonic measure. But since the harmonic measure has full support, that means that U equal to Ux on a full measure set, that means that set is dense, right? Any full measure set is dense because this has full support, and U is continuous. Therefore, by continuity, U equals to Ux on the full boundary of the ball. All right?
Right.
Yes. So this is true for all radii sufficiently small. So therefore, on every sufficiently small geodesic sphere, U is equal to Ux. So that means U is equal to Ux in a neighborhood of X, right? And therefore, that means this set E is open. And so it's open, closed, and non-empty. So therefore, it's the whole domain. And so U is equal to constant M. Is this okay?
Yes, sir.
Yeah. So it's just like the proof of the strong maximum principle in Rn, just that we used the submean value property with respect to harmonic measure instead of the usual submean value property in Rn, right? That's all. Yeah. You just replace the Lebesgue measures on the spheres by harmonic measures, and then the same proof goes through. Okay. Okay. So that's the strong maximum principle. And as usual, the strong maximum principle implies the weak maximum principle. So let D again be a precompact domain, and let U be C2 on D and C0 on D closure, and let U be subharmonic on D. Then the supremum of U over the domain D is equal to the supremum of U over the boundary of D. So U attains its maximum on the boundary. And the proof is just the same as in the classical case. So let X naught be a point in D closure where U attains its maximum. If X naught belongs to boundary D, then we're done. Otherwise, X naught belongs to D. And then by the strong maximum principle, U is constant on D. And so therefore, if it's constant, the SOP over D is the same as the SOP over boundary D. Okay. So, yeah, I think Rudra, you asked why, this is called weak maximum principle and that is strong. I think it's because of this, because the strong maximum principle implies the weak maximum principle.
Oh.
So this
Okay,
proof,
yeah.
right, it just shows that the strong maximum principle always
Right.
implies the weak maximum principle. So that's why, yeah, the name. And also the proof of the strong maximum principle in general is harder than that of the weak maximum principle. Yeah. Even in Rn, for general elliptic operators, the proof is quite involved of the strong maximum principle. Okay. So there are 3 minutes left in this session. Let me not rush. Are there any questions or comments at this point? So what we're going to do after this is we're going to prove the Dirichlet problem is solvable for a we're going to talk about the solution of the Dirichlet problem for a precompact domain with C2 boundary in any Riemannian manifold. Okay. That's what. So we're going to use the Perron method, the classical Perron method, to prove that. That's what we're going to do. So since there's just 2 minutes left, I don't want to start, talking now about it. So if you have questions, I can, or comments, we can talk about that.
The soft arguments are very close to Euclidean, isn't it?
Exactly. Yes. That is why I chose these soft arguments, because they're very similar to the Euclidean. Yeah, exactly. The only, where instead of in Euclidean space, you have the submean value property with respect to Euclidean measure, I mean Lebesgue measure.
Right.
Here, you have the submean value property with respect to harmonic measure. And then the same arguments go through, right? So just using the submean value property. So whatever you can prove using submean value property, more or less it should go through if you replace Lebesgue measure by harmonic measure.
Right.
That's the idea. Yeah. So, yeah, there is one also fact, I think, which Utsav mentioned that, or maybe Rudra, you said that the harmonic measures are equal to the Lebesgue measures if and only if the manifold is harmonic. So that, yeah, I don't know the proof of that. One direction we've proved that if the manifold is harmonic, then the harmonic measure is equal to the Lebesgue measure. But the converse, I don't know. Yeah, I don't know about the converse. I'll have to look it up. Yeah, but that's a nice. I think that's true. I think that's true. I think that's true. Okay, let me stop this session and we'll just take a 2-minute break and then we'll come back for the next session. Okay. 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 So we've got the strong and weak maximum principles for C2 subharmonic functions in arbitrary precompact domains in a Riemannian manifold. So now we're going to start talking about the Perron method. So for that, we will need a more flexible definition of subharmonic and superharmonic functions, which works for continuous functions. Okay. So that's motivated by the following. So first of all, we proved the weak maximum principle for a domain. That means a connected open set, but with whose closure is compact. But this will also work for any open set whose closure is compact. Right? You follow the same argument. You take a point in the closure of the open set where U attains its maximum. If it's in the boundary, then we're done. Otherwise, it's in the domain. It's in the open set. So then U will be constant on the connected component of the domain containing the point x0. And then that means it will be constant on the boundary of that connected component, which is contained in the boundary of the open set. And so therefore the supremum will be attained on the boundary as well. Is that okay? Yeah?
Yes. Yes.
Okay, so you don't need connectedness as such. You just apply the same argument to a connected component of the open set, and that will give you the result as well. Okay. Yeah. So now suppose D is an open set in M, and suppose U is C2 and subharmonic. Okay. So let U be an open set in D such that U closure is compact and contained in D. Okay. Then if I take any function H, oh, I forgot to say, which is harmonic in U. Okay, so it's C2 in U and continuous on the U closure, and H is harmonic. I forgot to write that, so sorry. So then if the subharmonic function U is less than or equal to H on the boundary of U, then U is less than or equal to H on the open set U, right? By the weak maximum principle. Since, I mean, U minus H will also be C2 and subharmonic, and U minus H is less than or equal to 0 on the boundary of U by hypothesis. So therefore, it's less than or equal to U 0 on U by the weak maximum principle, right? So that means that a subharmonic function satisfies this property whenever you take an open set with compact closure inside your domain, and if you take a harmonic function which is greater than or equal to your subharmonic function on the boundary of that domain, then it is on the boundary of that open set, then it is greater than or equal to the subharmonic function on the whole open set, right? So subharmonic functions are dominated by harmonic functions with the same boundary values. Hence, again, the name subharmonic, right? Meaning below harmonic. It's bounded above by a harmonic function. So this property that we've proved here, this we can actually take as a definition for continuous functions, as a definition of subharmonicity. Right? So we take the following definition. So suppose D is a open set in M, and we say a continuous function on D is subharmonic on D if whenever U in D is a precompact open set whose closure is contained in D, then if we take any H, which is C2 on U and C0 on U closure and harmonic in U, if H is greater than or equal to little u on the boundary of U, then H is greater than or equal to U on the open set U. All right. So we're taking this property of C2 subharmonic functions, we're taking it as a definition of subharmonicity for continuous functions. All right.
Okay.
Is the definition clear? So
Yes.
let me just draw a picture.
Yeah.
And that will help. So we have some let's say some domain D like this. This is my domain D in my Riemannian manifold. And then the property is that whenever I take an open set with compact closure contained inside my domain D, this is my U. This domain is my domain D in M. If I take H here, H is a harmonic function which is greater than or equal to little u on boundary U, then this implies that H is greater than or equal to U on all of U. Okay, so this is the property that we want. So is it clear? Yeah. So this implies, in particular, if I take U to be a ball, right? If I take U to be a ball, then I will get the submean value property in this ball with respect to harmonic measure. Or basically what I can do is I take U restricted to the boundary of this ball, right? So if I take a ball B, I take U restricted to boundary B, and then I choose H harmonic on, yeah, the harmonic extension of this U restricted to boundary B. So I choose H harmonic on B such that H restricted to boundary B is equal to U restricted to boundary B. So then the definition of subharmonic that we're taking here, that will imply that U at any point X is less than or equal to H of X, which is equal to the integral over boundary B of U xi d mu xb of z for all x in B. Right? So you will satisfy the submean value property with respect to balls. Is this clear? Yeah. So once you have this, then you'll get, by the same argument as before, that a continuous subharmonic function also satisfies the strong maximum principle and therefore also the weak maximum principle. Is that clear? The same proof as before. All we used was this submean value property with respect to harmonic measure on balls, right? That's all we needed for the proof of the strong maximum principle. Okay. So this definition of this definition of subharmonic for continuous functions, these continuous subharmonic functions will also satisfy the strong and weak maximum principles. Okay, and we say that U is superharmonic on D if minus U is subharmonic on D. Okay, so I mean, superharmonic, the definition will become reversed actually. What happens is, if H is a harmonic function which is less than or equal to U on the boundary of this open set U, then H will be less than or equal to U inside the open set U, right? So superharmonic functions lie above harmonic functions with the same boundary values. So I mean, in one dimension, this you can see, right? Literally, a harmonic function once you give its boundary values, then it's determined uniquely inside. It's just the straight line. And in one dimension, subharmonic means convex. So a convex function which is less than or equal to this harmonic function at the endpoints will have to stay less than or equal to it inside, right? And superharmonic means concave. So a concave function which is greater than the harmonic function will stay greater than it here, right?
Yes.
That's it. So this makes sense for continuous functions, right? Just like convexity is a notion which makes sense for continuous functions, right? You don't need C2 for to define convexity, right? Similarly, for subharmonicity, you don't need C2. It makes sense for continuous functions. Okay. I mean the advantage of using continuous functions is then you get more flexible constructions of subharmonic functions, right? So for example, if I take two subharmonic functions, right, then their maximum, which is this function, will also be subharmonic, right? So if this is, say, u1 and this is u2, then this function, which is max of u1, u2, this will also be subharmonic, right? It's just like the fact that a maximum of convex functions is convex, right? So that is easy to prove, right? So
By
because
submean value.
if H, no, you use the definition, just use the definition. If H is greater than or equal to U, which is the max of U1, U2, on boundary U, okay, so then that means what? H is greater than or equal to U1 and U2 on boundary U, but U1, U2 are continuous subharmonic. That means by definition that H is greater than or equal to U1, U2 on U, right? Because U1, U2 are subharmonic.
Yes.
And that implies H is greater than or equal to the maximum. So that's it. It's just a one-line proof. Okay.
Yes, sir.
That's it. Yeah. Yeah. So this is why it's good to have this definition for continuous functions, because see, the maximum of C2 functions in general will not be C2, right? As you can see in this example, the maximum is going to have points where it may not be differentiable, right? Where the two graphs intersect, it may not be differentiable at those points. So, but it's still going to be subharmonic. Okay? And this is useful for us when we do, when we study the Perron method. Okay. So notice that we've already shown that if U is C2 and Laplacian U is greater than or equal to 0, then U satisfies this new definition of subharmonic, right? This we've already shown. Okay, we've shown this. And okay, as I just remarked, it's easy to see that if U1, U2 are continuous subharmonic functions, then the max of U1, U2 is also continuous and subharmonic. Okay. And now, as I was saying a couple of classes ago, for the Perron method, we will need the notion of harmonic lifting of a subharmonic function. Right. So this means you take a continuous subharmonic function and you take a ball B in the domain D, geodesic ball, whose closure is contained in D. And then you look at U restricted to the boundary of this ball and then take its harmonic extension into the ball, right? So that means H is C2 in the ball and C0 on the closure, and is the solution of the Dirichlet problem, Laplacian H equal to 0 in B and H equal to 0 on boundary B. Okay. So then the harmonic lifting of U with respect to the ball B is the function U sub B. Okay. This is again going to be a continuous function on the domain D, where U sub B of X is just U of X if X is in D minus B closure, and H of X, this harmonic function, if X is in B closure. Okay. So, first note that by the definition of subharmonicity, this harmonic extension H is going to be greater than or equal to U on the ball B, right? Because it's equal to U on the boundary. And so by definition of subharmonicity for continuous functions, it's going to be greater than or equal to U inside the ball B. So that means that this harmonic lifting is always greater than or equal to U, right? Because outside the ball, it's equal to U. Inside the ball, it's greater than or equal to U. Okay. So the harmonic lifting is always greater than or equal to U. Okay, so I mean, in the picture, the harmonic lifting would just be this picture. You have your subharmonic function, and then you take a ball in the domain that's like an interval here, and you replace the subharmonic function by the harmonic extension, right? So the harmonic lifting would be this function. Right? So that is, of course, greater than or equal to the original function, right?
But still,
This is the
still it is subharmonic, right?
right. So that we're going to prove now. Yeah, still it is subharmonic. So we need a proof of that. So let's prove that. Yeah, we need the fact that it's still subharmonic, right? So let us prove that. So that's the following lemma. The harmonic lifting is subharmonic. So continuous is clear. We just have to prove the definition of subharmonicity. So let U be a precompact open set such that U closure is contained in D, and let H be C2 in U, C0 on U closure, and harmonic in U, such that H is greater than or equal to the harmonic lifting U sub B on the boundary of U. Okay. So then H is greater than or equal to U sub B, which is greater than or equal to U on the boundary of U, and U is subharmonic. Therefore, by definition, H is greater than or equal to U, right? On the open set capital U, because little u is subharmonic. So that implies that H is going to be greater than or equal to U sub B on U minus B closure, because U sub B is equal to U on U minus B closure, right? So we want to show that H is greater than or equal to U sub B on all of U, but we've got it on U minus B closure. So now we have to show that H is greater than or equal to U sub B on U intersect B, right? Yeah, so here's the picture. We have our domain D. Now we did our harmonic lifting on some ball B. Okay. And now I'm taking some arbitrary open set with closure contained in D, U. Okay. So outside this ball B, here I have that H is greater than or equal to U, which is equal to U sub B here. Is this all right? Yeah. Outside this ball B. So I just need to show H is greater than or equal to U sub B over here in the intersection, right? So what is the boundary of the intersection? So there'll be a part coming from boundary B and there'll be a part coming from boundary U, right? Yeah. So notice that the boundary of U intersection B is contained in boundary U union boundary B, right? So let X be a point in the boundary of U intersect B. So if X belongs to boundary U, then by hypothesis, HX is greater than or equal to UB of X, right? We're assuming that H is greater than or equal to UB on the boundary of U. Okay. So that means if I take this point in boundary of U intersect B, if H belongs to boundary U, then H is greater than or equal to UB X. Okay. Now, otherwise, H belongs to boundary B minus boundary U, right? And X belongs to U closure. Okay. Hence, X belongs to U, right? So, because X is not in boundary U and it is in U closure, therefore it is in U, right? So that means that HX is greater than or equal to UX and UX is equal to UBX because X is in boundary B, right? On the boundary of the ball B, by definition, UB is equal to U. So therefore, in this case also, HX is greater than or equal to UBX. So what do we get? We get that H is greater than or equal to this harmonic lifting UB on the boundary of U intersect B. And since UB is harmonic on U intersect B and H is harmonic on U intersect B, therefore, by the maximum principle for harmonic functions, H is greater than or equal to UB on U intersect B. Okay, so we're done. Is that all right? Yeah.
Yes, sir.
Yeah. Yeah, I mean, so in this picture, basically, there were two cases. When you're in this is U intersect B. And this part, this is in boundary U. So if you're on boundary U, then over here, we know that H by hypothesis is greater than or equal to UB. Otherwise, we're on boundary B, but then I know that H is already greater than or equal to U. And so then over here, H is greater than or equal to U, and U is equal to U sub B on this boundary. So H is greater than or equal to U sub B here. Sorry, one second. Okay, so therefore H is greater than or equal to U sub B on the boundary of U intersect B, and therefore by the maximum principle for harmonic functions, it's greater than or equal to U sub B inside, and that's it. Okay, fine. So this harmonic lifting is subharmonic. Okay, so now we can come to the Perron method. Okay, right. So the first lemma is that if U is a continuous subharmonic function, then U satisfies the strong maximum principle. Okay, so this, as I said, this follows from the sub-mean value property with respect to harmonic measure, right? So I don't know what proof I've written here. I think that's basically the same proof that I've written here. Yeah. Yeah, I mean, yeah, it's basically the same proof. So Right. So okay. Well, I've written it in terms of the harmonic liftings, but conceptually, maybe it's simpler just to think about it in terms of what we observed here, that a continuous subharmonic function also satisfies the submean value property with respect to harmonic measure, right? If you use that, then the strong maximum principle follows with exactly the same proof, right? So the strong maximum principle is true. So you can look at this proof if you want. I'm not going to go through it, but I mean, I think it's essentially the same proof, just written in terms of harmonic liftings. Okay. Is this all right? So I'm skipping this proof.
Yes.
Yeah.
Yes, sir.
So as before, the strong maximum principle implies the weak maximum principle. Okay. Fine. So that proof is the same as before. A strong maximum implies weak maximum. All right. So now we can finally come to the Perron method, right? So let D be a precompact domain in M, and let phi be a continuous function on the boundary of D. So we want to solve the Dirichlet problem, right? We want a function which is harmonic in D, continuous in D closure, and is equal to phi on the boundary of D. In other words, we want to extend phi to a harmonic function on the domain D. Right? We want a harmonic extension. So we define the Perron family to be the family of subharmonic functions f sub phi, which are functions u which are continuous in the closure of the domain, such that u is subharmonic on D and u is less than or equal to phi on the boundary of D. Okay. So these will look like well, maybe I should try drawing a picture in 2 dimensions, even though it's a bit harder. So yeah, I mean, okay, so maybe the graph of U looks something like this. It's a bad picture. Anyway, so this is maybe the graph of phi, right? Sitting over the boundary of your domain D. This is boundary D. Yeah, and then, so you want subharmonic functions which are less than or equal to phi on the boundary. So their graphs will look something like this. Let's say you could take a convex function like this. Right? Okay.
Yes.
Yeah, this is going to be subharmonic and less than or equal to phi on the boundary. Something like this. Okay. Of course, this family of functions, f phi, the Perron family, so subharmonic and u less than or equal to phi on boundary D. This is always non-empty because phi is a continuous function on the compact boundary. So it's bounded below. So you can always just take any function which is less than or equal to the infimum of phi, right? You can just take the constant function, right? If I take a constant phi u equal to constant infimum of phi, right? Infimum over boundary D of phi. This belongs to the Perron family, right? So this family is always non-empty. Okay. Now to try and solve the Dirichlet problem, what we want to do is try and take the maximum of such functions, right? So we'll try and take, larger and larger such functions. Okay. So I mean, actually, this is better seen in one dimension, as we discussed in an earlier class, right? Here is the harmonic extension of the boundary values. And then we're looking at all these subharmonic functions, which are less than or equal to the boundary values. And then when you take a supremum over them, you get the harmonic extension, right? Okay. So that's the idea here. First we note that by the weak maximum principle for subharmonic functions, for any u which is in this Perron family, u is less than or equal to the sup of phi for all x in D, right? By the weak maximum principle. So therefore, the functions u are uniformly bounded above by a constant, right? Therefore, we can define what's called the Perron solution. This is the function u phi of x is the supremum over u in this Perron family of u of x. Okay. So since these u's are all uniformly bounded above by a constant, this supremum is finite. Okay, so this is well defined. And since all of the u's are bounded above by the sup of phi, this u sub phi is also going to be bounded above by the supremum of phi. And since the constant function inf of phi belongs to the Perron family, this u sub phi will also be greater than or equal to the inf of phi, right? Okay, so this will be bounded above and below this Perron solution by the infimum and supremum of phi. Is this okay? Yeah.
Yes, sir.
So now what do we want to show? We want to show that the Perron solution is harmonic in D, right? So see, as I remarked in a previous class, that if this Perron solution is continuous, then it's easy to show that it's harmonic. Right. So, if the Perron solution was continuous, right, then what could you do? You take any ball in the domain, right? And then you take the Perron solution. So, if it's continuous, then it will also be subharmonic, because the same argument, the supremum of subharmonic functions will be subharmonic. Okay. So then u will be subharmonic, this u phi, and now you take the harmonic lifting of this Perron solution in this ball, right? So the harmonic lifting, so if I take the harmonic lifting of u sub phi, right, this will be greater than or equal to u sub phi, right? The harmonic lifting always increases the function, but by definition of the Perron solution, this is also subharmonic. So this will be less than or equal to u sub phi, right? Yes. So therefore, the two will be equal. Is it clear? And so that means u sub phi will be equal to its harmonic lifting, which is harmonic in this ball, right? And so therefore, the Perron solution will be harmonic in any ball, and so it's harmonic everywhere. Okay.
Yes.
That's the idea that we could do if u was if the Perron solution was continuous. The problem is continuity, right? So that's the problem. So we have to work around that slightly. So okay, so maybe the proof is a little long, so maybe there's only about 4 minutes left. Let me do the proof tomorrow. Okay. So instead of rushing it, so yeah, so if you want to discuss anything or any comments, then we can do that now.
Kingshuk?
Yes.
Yeah. So I'm saying, can you summarize a bit about this last part? That what is the target at this moment of
Okay.
using this Perron's family?
Yes, yes. Okay, fine. So, so we've defined the Perron solution, which is given by taking pointwise the supremum over the Perron family, right? So U sub phi of x is the sup over U in F phi in this Perron family of U of x. Okay. So what we want to show is that actually this is the solution to the Dirichlet problem. So we want to show first that U sub phi is harmonic in D. So what I was saying is this is easy if U sub phi is continuous,
Right.
right? But the problem is we don't know it's continuous because it's a supremum of a family of functions. It may not be continuous, right? It's just semi-continuous in general. So that's a something we have to deal with. And once we do that, then what we want to show is that U sub phi of x, it has the right boundary values. This converges to phi of xi as x converges to a point xi in the boundary of T. So there are these two separate statements we have to prove. So the first statement, this is always true, that the Perron solution is always harmonic. But the fact that it has the right boundary values, this needs some regularity of the boundary of D. Otherwise, in general, it's not true. So this needs some regularity of boundary D. Yes, so C2 is good enough. C2 is good enough. Okay, so that's what we want to do. So we'll do both of these tomorrow then. Okay.
Okay.
Yeah. So see you tomorrow.